Okay. We have been considering discrete time random processes and then wide sense stationary random process, their correlation structure. In fact, we have shown in the last class that correlation and covariance matrices assume a special structure called Toeplitz, where the diagonal entries are same, sub-diagonal entries are same, and like that. Okay. Those matrices have been studied extensively. Many algorithms have been devised to invert these matrices or solve special equations involving these matrices like that. Okay. That we will not cover in this course, but Toeplitz matrices had been very popular and have been widely studied, extensively studied in 80s, 70s and also 90s. Okay. We will cover something called power spectral density today. This is valid only for a wide sense stationary process. We have seen for WSS xn Rxx autocorrelation Rxsk is xn x star n minus k, right. So, it depends only on the gap between the two indices n and n minus k, that is how close or how far they are usually. So, that gap is k, so it is a function of k. But then Rxsk then becomes a sequence, because k is 0, k can be 1, k can be 2, k can be minus 1, minus 2 like that. So, here Rxx 0, Rxx 1, Rxx 2, Rxx minus 1, Rxx minus 2 like that. So, it is a sequence. So, Rxk can be, you can plot Rxx k. So, this axis is k, you can have various values Rxx 0 dot like that. The moment you have a sequence, then it comes to my mind, well, if I take the discrete time Fourier transform DTFT of this, what do I get? What is the meaning of that? So, let phi xx e to the power j omega be the DTFT. When you write DTFT, discrete time Fourier transform, we write in the form of e to the power j omega, where omega is the variable, E is a constant, J is a constant, but still we write like this, because DTFT is a power series summation where powers of this e to the power j omega comes. We will see it. So, DTFT of Rxxk or maybe Rxxn, does not matter which index you put. Like this is the formula which you are familiar with in DSP, Rxxn e to the power minus j omega n, n from minus infinity to infinity. So, all powers of e to the power j omega, positive and negative powers. So, it is a power series, that is why we write in the form of phi x e to the power j omega. The actual variable is omega, it is a function of omega, because E is a constant, J is a constant. All right. Now, what is the meaning of this? That is what we have to see. What is the meaning of this? If this is the DTFT, inverse DTFT will give me this guy Rxx at a particular n of your choice, n is fixed here, n is of your choice. For that n, you have to carry out this integral, inverse DTFT integral. You have studied in DSP. This quantity e to the power plus j omega n, this n is fixed here, n comes from outside. For that n, we carry out the integral with respect to omega. All right, this is Rxxn. If this is the DTFT, this is the inverse DTFT. Then what is Rxx 0? And Rxx 0, remember, is equivalent to what? E of xn x star n, k is 0, so E of mod xn square, and if xn is 0 mean, it is the variance. Variance is average power. Okay. If k it is not 0 mean, it will be E of mod xn square, means expected value of the total power at any index n, n does not matter because of wide sense stationarity. So, sigma x square, when say is 0 mean. So, x n is itself is the increment or decrement, and therefore, it is expected value of the power of the increment. So, it is variance, but that by this integral will be, you put n equal to 0, c to the power 0 1, that means this is such a function which when integrated over the entire range minus pi to pi, you remember DTFT is periodic over a range minus pi to pi. Whatever you see in minus pi to pi, that gets repeated both in magnitude sense and phase sense. So, this function, it is just the integral. So, total area under this gives you the average power. Okay. It is like, and we will soon see that this is actually non-negative, that also we will see. This is real, not negative. Okay. Before I say something about its physical interpretation, let me first prove them, then I will come to this expression again. Let us see phi xs into the power j omega. I am repeating that same statement. Remember, the other day I told you about one property, Hermitian property of this thing, autocorrelation function. Rxxn is same as Rxx star minus n. That is why the autocorrelation matrix is, or correlation matrix is conjugate symmetric, triplete and conjugate symmetric. Okay. So, this summation I divide into 3 parts. One is n equal to 0 e to the power 0. So, Rxx 0. And remember, Rxx 0 is variance, which is always real and non-negative. Variance e to the power mod x n whole square. Mod x n square makes it non-negative, a real and expected value. So, it is a real stuff. Then one summation I take over the positive range 1 to infinity, and another summation I take over the negative range minus infinity to minus 1. Or maybe better if I write this minus 1 to minus infinity. It does not matter whether you start at minus 1 and go up to minus infinity, or start at minus infinity and go up to minus 1, you cover the same points. But I prefer this, and then same expression Rxx n to the power minus j omega n. Here n if I replace by minus n, then what will happen? I have a Rxx minus n e to the power plus j omega n, and if it is n equal to n, if I replace minus n, then n will be from 1 to infinity. Okay. So, minus n equal to minus 1 means n will be 1, minus n equal to minus infinity means n will be infinity. Or if you still do not understand, you can call it minus m. Say, so it will be Rxx minus m, it will be e to the power plus j omega m, and summation when n is minus 1, m is plus 1, and when n is minus infinity, m is plus infinity. And it does not matter whether you write, I mean whether the index is m or l or r or k, anything. So, I can as well write n here, n. So, if I do that, and remember Rxx minus m is Rxx star minus n is Rxx n. So, if I apply star on both sides, star goes from here. So, Rxx minus m will be Rxx star m. So, if I put it here, then n equal to 1 to infinity, this summation is there, Rxx n e to the power minus j omega n, and another one same range, now 1 to infinity. Instead of m, I again bring n, and so r x x minus n means r x x star n, and e to the power j omega n. Instead of m, again I am writing in terms of n. So, these two things, same range of summation. If you call this z, you can see this is z star. R x x n e to the power minus j omega n. If you apply conjugate on this, conjugate on a product of complex numbers is product of conjugated complex numbers. So, it will be r x x star n, which I have here, e to the power plus j omega n, which I have here. So, if it is z, it is z star, and any z plus z star is twice real part of z, which is real. So, this will be twice 2 will go outside the summation, real part. So, the real part of z. So, this is your z, z plus z star, that is twice real part of z. Okay. So, this is real, this is real. So, this whole thing is real. That is what I said, phi x x e to the power j omega is a real function. Okay. We will also show little later that it is actually non-negative. Now, coming to the previous page, this was r x x 0. R x x 0 was the average power. Okay. And this real function is such when integrated over the entire range of the DTFT from minus pi to pi, because DTFT is periodic from minus pi to pi over a period of 2 pi. So, if I integrate this function, this area, function over that range, then this scale factor, it gives me power. That means, so if I have something like this, then area under this will give me the total power. Okay. And if I take any point omega and very small width d omega. Okay. So, if d omega is very small, then function does not change appreciably within that. So, height is almost like constant, it will be phi e to the power j omega. Okay. So, area under this will be this into d omega. Okay. And total area will be just, that is total power will be, I will forget about this 1 by 2 pi, it is just a scale factor. It will be just summation of this over all such small slots. There is a definite integral, it will be integral. So, that is why this is called power spectral density. This times d omega gives you the distribution of r x x 0 that lies in the small band at omega, omega to omega plus d omega. Their power, you see, after all, if it is very small, then we can say that the power, the fraction of the power, average power lying in the band will be linearly proportional to this width, because larger the width, more will be the power, and linearly proportional because it is very small. So, in the while keeping it very small, if d omega increases in the band, fraction of the power in that band will increase and vice versa. So, it is linearly proportional to d omega. So, proportionality constant is this, which is a function of where this slot d omega is located. Okay, that is at omega. So, this function value at that point. Okay, so, this is called actually power spectral density, because this times d omega gives you I mean this is easier to understand this way. This time d omega gives you the fraction of the power at this small band located at omega to omega plus d omega. Assuming the function does not change, it is just the rectangle kind of stuff, area under the rectangle is this. That will give you the fraction of the power in that small band of width dw d omega at the point omega. Okay. So, that is why this is called density. This times d omega gives you that power. This times d omega gives you the power. Okay. So, it is density. Okay. So, this is the power spectral density, and when you integrate it and multiply by 1 by 2 pi, integrate from minus pi to pi, you get the total power spectral, I mean average power. All right. So, this is the power spectral density. Which one? This one. This is PSD. Density, because you have to multiply by d omega, width. Then you get the area of this, which is the power within this band, and then integrate, you get the total power. Now, we have shown that this is real, we will also show that this is non-negative. For that, some other result is required, which we will do now. Suppose I have one x n which is 0 mean, not 0 mean may not be necessary. So, let me not take that, make that assumption, which is just WSS. It is going into LTI, linear time invariant system, which is characterized by impulse response or unit sample response, and output y n you know is convolution between this and this. This convolution you can write in 2 OS, it is same as H n star A x n. So, H R x n is your choice, it is fixed, R is a summation index in the summation. So, R is just local variable, H R x n minus R. But this is also actually x n, we have seen x n H n, this is also equivalent to, in fact, n minus R if you replace by m, R is n minus m. So, this becomes n minus m, this becomes m, and range from plus infinity to minus infinity, which will give you the same result if it is from minus infinity to plus infinity. Okay, so, you get the same thing. So, here these things you have studied in DSP, that is why I am not speaking much on this, because these are not really focus of the lecture. X comes first, so x will have the index with only R, like H was first here, H n star x n. So, H got R, this guy x got n minus R. So, here x got R, H gets n minus R. All right. But between the two, it is this form which is always very useful, not this. Okay, this is the form which is very useful. I mean, originally convolution comes this way, then we show by taking n minus R to be m, or R is n minus m, H R x n minus H m x n minus m, and m from plus infinity to minus infinity, which is same as m minus infinity to plus infinity, because the range is same, and then it becomes this summation. M you can replace by R, you get this summation. So, both are same, but this is in practice more useful. I mean, if you choose this form, it is easier to solve problems. Anyway, my point is input is random, every sample is a random variable. In this convolution, you are summing, you are multiplying every sample by an H value and adding them. So, this entire thing which is y n, that is also random, because H0 xn, H1 xn minus 1, H2 xn minus 2, H minus 1 xn plus 1 dot dot dot. So, you are linearly combining, that is multiplying every random sample of x by some constant and adding. Since samples of x are random, the summation which is yn, that is also random. If that be, then the question is, if input is WSS, is yn also WSS? Question. We will see, answer is yes. First, WSS means mean, mu y. It will be expected value of this summation. It is a summation like H0 xn, H1 xn minus 1, H2 xn minus 2 dot dot dot, E over all of them. We have seen E is linear, that is E of the summation will be same as you can push E on each random variable. So, it will be E on each, sorry, E will work directly on this. This is not random. So, this is deterministic constant, that times a random variable E on that, and E on a summation means E have to apply E on every component in the summation, and over this component, I mean this is a just scalar, non-random. So, E will not come over, E will come on the random part. Okay. And we know this is WSS, its mean is mu. This is the expected value of x n minus r, but x n is a WSS process. So, its mean is mu independent of what is this index, it does not depend on the index. So, E of this will be mu, say mu x. So, it will not be a function of n or r, because it is WSS, wide sense stationary. So, mean does not depend on the index, it is same everywhere. And then the mu x you can take out as common. Since H is a given sequence, unit sample response or impulse response sequence that you are adding, there is nothing random here and it does not depend on the index, okay, n. It does not depend on the index n. So, you get a constant here and this is a constant. So, constant independent of n. Means yn is first order stationary. That is its mean E of yn does not depend on n. Where is n? Because n has gone from here. Mu x is a constant, the mean for all the random variables same, and this is just a summation of the impulse response. Impulse response is known, summation is can be computed once for all, so it is a scalar number, this into mean. So, it does not depend on the index n, and that is why it is stationary in the first order, that is in the sense of mean. That is here also for yn, that is mean will not depend on what index you are choosing n, it will be same everywhere, and that is mu y, which is given by this constant. And then we come to the second order, there is a correlation of yn. Or y k, there is at a gap of k. So, yn y star n minus k, all right. And now, yn, go to the previous page, we chose this hr x n minus r, summation over r, hr x n minus r. this form. H gets just the index and x gets n minus that index. This H convolved with x, that kind of form. I have put n here, so this is by yn, and y star n minus k, another summation. Okay, H will come first and x will go second. No need to choose the same index r, okay, because this is independent of this, so choose L, HL, x n minus r minus L and then star. So, n minus r, n minus k, because this is n minus k, so n minus k. Okay. And yn, so that is n here, n minus k, so this index is n minus k. Okay. This you have to work out. The star on a summation of say complex numbers. As I have been telling again and again, conjugation of a summation of complex number means inside the summation every such complex number has to be conjugated. And but this is a product of two numbers. So, conjugate of a product we know, like Z1 Z2 star is Z1 star Z2 star. So, essentially it will be H star L x star n minus k minus L. All right. Then this is the random part, this is the random part. Okay. So, suppose this is a this is y star n minus k, okay, as we know. Now, this I can push inside this summation. This is the word r, this is y star n minus k. It does not depend on r. I can push inside the summation, multiply with this. Okay, instead of that means instead of carrying out this first and then multiplying with by this, I can push inside this summation. On every such product, I further multiply by this and then add. I will get the same thing. But that means this into this, y star n minus k, that has n, and x n minus r, that are n. I club them together, that product, then multiplied by hr, then this. If I do that, it is this part y star n minus k, and y star I write like this. And again here, instead of carrying out the summation first and then multiplying by this, I can push this inside. So, every such product I further multiply by x n minus r and then add. Okay, and then this and this I club together under one bracket. So, this will be E of then this summation H L, okay, and x n minus r I have pushed in n minus r and x n minus k minus L star. So, there will be star on this also, because star was over the product. So, Z1 Z2, Z1 star, Z2 star. Instead of putting the star here, let me Okay. Now, what does it mean? Every time you take an R, put an HR, then take all values of L. For each L, carry out the product. And then you have to apply and then do again another R, and for that R again within bracket carry out the sum. So, you got a huge sum and expected value of each, means expected value you can push inside the sum, and only these are random, these are not random. So, E will finally come here. Okay. Because it is a huge sum of product of two random variables multiplied by some scalars and summed and summed. So, E outside. So, E will be working on and every such term only the product of the random part. Okay. These are not random. So, E comes directly on this part, and you see this is nothing but correlation, autocorrelation or correlation. This is one index of x, this is another index. So, gap between the two indices is this index minus this index, n minus r and n minus k minus l. So, if you subtract this from this, it will be k plus l minus r. So, this is nothing but autocorrelation r x x k plus l minus r. All right. Now, you see this from this entire sum n has gone, there is no n. K was the gap, and indeed it is a function of k. L, you sum over L, so L goes after the summation. R also another summation index, you sum over R, so R also goes. Okay, because you are putting all values of R and adding, you are putting all values of L and adding. So, in the end, L and R will go, it will be only a function of k. So, it is also, I mean, this correlation also depends only on the gap between the two. Therefore, this is a function of k means yn stationary in second order also. Second order means correlation. So, together first order and second order stationary implies yn weights and stationary. So, I stop here now, and from here I will just answer this question in the next lecture, that okay, yn also WSS, what will be power spectral density of yn in terms of the power spectral density of the input and also the impulse response. That is what I will derive in the next class. Thank you very much.